So one question you may be wondering is, if we can just simulate these quantum algorithms on a classical computer, like I've been doing in this web browser version, then why do we need a quantum computer at all? So, while it's true that quantum computers don't violate the Church-Turing thesis, which is to say a classical computer can simulate any computable algorithm, including the quantum ones we've been looking at, there are some limitations that classical computers have when calculating quantum algorithms that quantum computers have a distinct advantage over. So in this video, I'm going to be exploring those differences and also some limitations of quantum computers as well, and then some of the advancements that actual quantum computer companies are doing. So to get a bit of a better idea of why exactly quantum computers are different than simulators, let's remember exactly what we're doing. So we have qubits, which can be in any different possible combination of 0 and 1, and we can represent this through Pauli matrices. Now this is a very simple one, where a qubit is either a 0 or a 1, so it's just like a bit in classical computing. You can see here the Pauli matrix is pretty simple. It's only 2 values. And then what we do is we apply gates to these qubits to change the states of them, the real and complex numbers, which gives us bigger matrices. Now, these gates are pretty simple. These are just for 1 qubit. But if you look at the Fredkin matrix, which is one for 3 qubits, we can see it gets pretty fast pretty quickly. So here what we're doing is we're representing qubits in superposition. So what a quantum computer does is it has all these different values for an input in different parallel universes. So it doesn't require too much memory. It's almost using the memory or the computational power of the parallel universes to do its calculations. So with a quantum simulator, what we're doing is we can also add these matrices together. We have the math to do it, but the problem is going to be the computational complexity when it comes to making these calculations, which is going to grow exponentially with the number of qubits you're working with. So here's the equation of the real numbers we'll need to do the calculation. And if it's 1, we only need 4 real numbers. But if it's 24, see, we're going to need a whole lot more amount of real numbers. However, even though quantum computers have a huge advantage when it comes to computational complexity over classical simulators, the major problem that it encounters is decoherence, which is to say when an outside state influences the qubit you want to work with, which will change their outcome and give you a result that's not correct. Now, what quantum computer companies do now is they try to create a vacuum inside of where the qubits are operating. So this vacuum's as close to absolute 0 as possible. You can't get to absolute 0 because that violates the third law of thermodynamics, but it's very, very cold in there, like less than 1 Kelvin degrees. So we can represent decoherence through this equation right here, which basically says that if you set up your experiment properly at the beginning, before you do your calculations, I and E, which is basically the qubits you want to make your calculations on, and the state of the outside world, is separate. You can see they're separated right here. But after the experiment, if we don't have good coherence, if we don't prevent decoherence, what happens is the 2 states combine right here, and your final outcome on the simulator is going to give you the wrong expectation value. So let's see an example of how this works on the quantum simulator. So if we were to run this algorithm, which is just the Deutsch-Jozsa algorithm, which we looked at earlier, we see that we get an expectation value of 25% for these values. So there's a 0% chance of it outputting all zeros and a 25% chance of these values. And if we look at all of them, there's also a couple more with the 0% chance of happening. But now let's look at a simulation that I ran on the IBM quantum computing cloud, where you build an algorithm and then they run it for you on their quantum computer and send you the results. And if we see the outcome, we see that for the most part, the values are correct. There's pretty much a 25% chance of each occurring, and about 25% of the outcomes did occur that we were looking for. But you can also see there's also a couple values that we weren't expecting to get, including all zeros, which means that this algorithm, this quantum computer, would give us a result that was the incorrect answer. Now, why is this happening? Well, if we look down here, we can see that they tell us what the fridge temperature was when they did this calculation, which is 0.01 Kelvin degrees, which is very, very cool, just about absolute zero. But it's not absolute zero, which means that there were other photons and other things in the state outside of the calculation we were making that were influencing the results and ended up giving us the wrong outcome at certain times. So the big enemy of quantum computing is decoherence, preventing the outside states from interfering with the qubits you want to do measurements on. And as the amount of qubits you want to work with gets bigger and bigger, it gets harder and harder to prevent decoherence. But as technology has been improving, quantum computing companies have been getting much better at it. So to give you a bit of an idea, D-Wave, which is a company based here in Burnaby, BC, which is the first company to produce a commercially available quantum computer, its first model in 2011, the D-Wave 1, could process 128 qubits. The D-Wave 2 in May 2013 could process 512 qubits. The D-Wave 2X, which was produced in August 2015, could process 1,152 qubits. And the D-Wave 2000Q, which was just produced this last January, it could process 2,048 qubits, which you can see is much bigger than the little 10 qubit simulator we've been working with. The calculations and the algorithms that you can run can get much more complex. You can solve answers to much bigger data. So a couple of cool companies that are using D-Wave's technology do exist. One that's quite interesting is Qubit, that's also based here in Vancouver. And it has on its website different algorithms you can run to solve problems, like the coloring problem, the clique cover, and the knapsack problem, which are all NP complete problems. So you can see as quantum computing advances, it's like D-Wave's computer and other quantum computers get better, the amount that we can do with quantum computers can have a profound effect on society and different things we can do, and different search algorithms we can run, like rovers, or things like factoring, like Scholl's algorithm, which could perhaps break encryptions for passwords in the internet. So these all just show the profound effect that quantum computers can have, and I hope, just like me, you're also quite excited about it.